Olá, pessoal. Boa tarde, tudo bem? Sejam bem-vindos ao segundo dia da CGESC, onde nós vamos começar agora a palestra do Dr. Girikonopasek, que ele gravou um vídeo para nós, e nós botamos a legenda e vamos apresentar ele aqui agora ao vivo, e depois do término do vídeo, ele vai entrar ao vivo com a gente para responder perguntas sobre o debate e a professora Luana vai nos ajudar a guiar esse debate também. Então, o nome do vídeo é Argumentos para o caráter amplamente intracontinental do orógeno Kaoko, Dom Feliciano, Gariep. O que aprendemos da geologia pré-Cambriana de Kaokoland, na Namíbia e do Estado de Santa Catarina, no Brasil. Girikonopasek possui doutorado em Petrologia Metamórfica e Tectônica pela Universidade Carolina de Praga. Atualmente ele trabalha no Departamento de Geociências da Universidade de Tromsø, na Noruega, atuando principalmente nas áreas de Petrologia Metamórfica, Geocronologia e Tectônica. Seus projetos atuais são a ruptura da rodinha registrada nos cinturões orogênicos neoproterozoicos do sudoeste da África e sudeste da América do Sul, e evolução convergente do sistema orogênico neoproterozoico do Atlântico Sul. Então, vou sair aqui, vou adicionar a transmissão dele e tenham um bom vídeo.
Hello, everybody, and thank you very much for joining in. My name is Jiří Konopasek, and I come from UIT, the Arctic University of Norway in Tromsø. And before I will start with my presentation, I would like to thank very much to the organizers for inviting me to this meeting and allowing me to present some of my research. As you can see on this slide, the title of my presentation is Arguments for Largely Intracontinental Character of the Kaoko Dom Feliciano Gariep Origin. And in this presentation, I will present some data that I have collected over many years in Namibia and also in southernmost Brazil. In the second half of the talk, I will also present data of my PhD student, Jack Percival, who is currently writing up his thesis at our university in Tromsø. My motivation for selecting this topic comes from the fact that me and my colleagues and friends, Karolina Cavalcante, Håkon Fossen, Vojta Janoušek, and some others, we have published some papers recently that question the subduction-related origin of the orogenic belts that we see exposed today along the eastern edge of the South American continent and also along the western edge of the southern part of Africa. So I would like to take this opportunity to present in person and maybe also a little bit more thoroughly our arguments for the intracontinental model that we have for this, what we call the South Atlantic Neoproterozoic orogenic system. In this presentation, I will first talk a little bit about the South Atlantic Neoproterozoic orogenic system itself and about the problem of the Adamastor Ocean, which appears in many tectonic reconstructions of this area. Then I will move into Namibia and will present the data for the pre-orogenic evolution in this part of the Kaoko, Dom Feliciano, and Gariep origin. Then I will present some data from Santa Catarina, the data of Jack Percival, which will be about orogenic evolution of the northern Kaoko, Dom Feliciano, and Gariep orogen in Brazil. And finally, I will draw some conclusions about the pre-orogenic setting of the southern South Atlantic Neoproterozoic orogenic system in general. Before I start, I would like to mention my collaborators. First of all, it is Charlie Hoffman from the Geological Survey of Namibia, then Jiří Sláma from the Academy of Sciences of the Czech Republic, Robert Anskiewicz from the Academy of Sciences of Poland, then my late friend with whom I worked at the University of Bergen, Jan Košler, some Czech colleagues, Stano Ulrich, Vojta Janoušek, Petr Jeřábek, and finally my Brazilian colleagues, namely Fatima Bittencourt and her PhD students Giuseppe De Toni and Matheus Battisti. So first, a little bit about what we call the South Atlantic Neoproterozoic orogenic system. This orogenic system involves the Araçuaí, Ribeira, and West Congo belt in the north, and the Dom Feliciano, Kaoko, and Gariep belts in the southern part. If we look at the existing models of the evolution of this entire orogenic system, we can see that they stress out the role of a large oceanic domain called the Adamastor Ocean, which was first defined by Hartnady et al. In 1985. And here, down in these two figures, you can see how the various authors imagine the pre-collisional or pre-orogenic setting of this entire area here. You can see that there are several subduction zones shown for the reconstruction of the Ribeira belt, for example, and also one subduction zone for the southern part of the orogenic system that represents the pre-orogenic convergent setting. However, these interpretations are problematic, and the problems that appear are not only related to the non-existence of any high-pressure rocks in the entire orogenic system in here, but also, especially in the northern part, the problem comes with the confined nature of the northern termination, where, in our opinion, it is really difficult to place any large-scale oceanic domain before the actual orogenic evolution. However, this is not the topic of my presentation today, and I will leave the northern part of the system out and will concentrate more on the southern part of the system, where the main problem for us with the subduction-related origin of this entire system in here is the short time span between the end of rifting and onset of convergence. So let's have a look at the southern part of the orogenic system, and here I will pose two main questions that I want to answer in this first part of my presentation. And these questions are: what was the pre-orogenic setting of the Kaoko, Dom Feliciano, and Gariep orogen? And the second question is whether the Adamastor Ocean really existed or not. So on this slide, I have placed several pre-orogenic reconstructions for the Kaoko, Dom Feliciano, and Gariep orogen. And you can see that they are very different, either in terms of the polarity of the inferred subduction, but also in terms of the actual duration of the subduction itself. So here you can see the model of Farid Chemale from 2012, where the subduction of the Adamastor Ocean is going towards the west, and the duration of the subduction process is estimated between 700 and 600 million years. In the second model, the model of Miguel Basset from 2018, you can see that the subduction of the oceanic plate goes towards the east, and the timing of the subduction is placed between 640 and 600 million years. Here, the model of Ben Goscombe and Dave Gray from 2007, again, the subduction going towards the west, but without any like a time interval for the subduction process. Finally, the reconstruction from the paper by Hartwig, Frimmel et al. From 2011, where you can see a rather complicated situation. But here, again, the position of the so-called Adamastor Ocean, they call it Brasilides in here, between the Luis Alves and the Angola block, and the duration of the entire system between 650 and 580 million years. So the question that I want to ask is how these time intervals inferred for the subduction, or for the timing of the subduction, how do they actually comply with the existing data? And for this, I will move into the northwestern Namibia and will show you some of my research that I did about the pre-orogenic evolution of the Kaoko belt. So, if we look at the Kaoko, Dom Feliciano, and Gariep orogen, the current models suggest continental breakup at approximately 780 million years ago. This is the work by Hartwig Frimmel and Miguel Basset and others again. And they also assume continental drift up to approximately 640 million years ago when the subduction starts, which leaves us with something like 140 million years of growth of the Adamastor Ocean. The same authors, they also assume approximately 40 to 50 million years of subduction, which is based on the age of granitoid rocks in the Dom Feliciano belt, in the so-called Granite Belt, which is interpreted as an arc domain. And these numbers are also related to the estimated onset of collision at approximately 600 million years. So, if we want to look at what these numbers mean in terms of the size of the oceanic domain, we can look at this graph that is shown in here, where on the horizontal axis we have the half spreading or subduction rate in millimeters per year, and on the vertical axis we have the width of the oceanic domain. And the graph is contoured for the duration of the spreading or of the subduction process. So in terms of the growth of the Adamastor, here we have the 140 million years. And for the spreading rate that we, or that existed for most of the time of the spreading of the Atlantic Ocean, which was about 20 millimeters per year, we will end up with the size of the Adamastor of something between 5,000 and 6,000 kilometers. If we take 40 to 50 million years of subduction, and we will say that the subduction goes with the rate similar to the spreading of 20 millimeters per year, we will see that the minimum size of the Adamastor Ocean must have been something like 2,000 kilometers. If we would have faster subduction, then of course, within this time span, we can consume even larger oceanic domain. My question is whether these numbers that are shown in here are actually compatible with the data about the timing of the breakup and about the timing of the extension that we see in the Kaoko and Dom Feliciano and Gariep origin. For this, I will, or in order to answer this question, I will take you to the Kaoko belt and will show you what do we know about the timing of the stretching of the continental crust, pre-orogenic extension, and about the possible timing of the actual continental breakup of the so-called Rodinia continent in this part of the orogenic system. So this is the geological map of the Kaoko belt in Namibia, and we will talk a little bit about these several orogenic zones that were defined already by several authors in the past. So the westernmost part of the Kaoko belt is called the coastal terrain, and it is representing now the orogenic hinterland, which has no basement older than approximately 800 million years exposed. And it is represented by migmatitic metasedimentary rocks with numerous bodies of bimodal metavolcanics. The volcanosedimentary sequence is intruded by granitoid rocks with the intrusion time spanning between 650 and 550 million years ago. We also know that the migmatization in the coastal terrain took place at approximately 650 to 630 million years ago, and the entire unit here, the entire coastal terrain, is interpreted by some authors as a late Neoproterozoic arc domain or a back arc basin. If we go farther to the east, we come into the orogenic foreland, and the orogenic foreland going from east to west is represented by eastern Kaoko zone, here shown in green, which is represented by rifting-related sediments and carbonate platform on top of the Congo crater, which shows only very weak Neoproterozoic deformation. The central Kaoko zone here in orange represent metamorphosed basinal part of the cover of the Congo crater, and in terms of the orogenic evolution, it represents a Barrovian type succession with metamorphic grade increasing from the green schist facies in the east up to the upper amphibolite facies in the west, here along this structure that is called the porous shear zone. The highest grade unit in the foreland is called the orogen core, and it is represented by migmatitic paleo to mesoproterozoic orthogneisses and metasedimentary rocks, which were migmatized at approximately 550 million years. And all these three units they somehow have an affinity to the Congo craton. So they have a Congo craton type basement and different types of extension or rifting related metasedimentary rocks that are sitting on top. If we look at the volcanosedimentary sequence of the coastal terrain, we see that the actual metasedimentary rocks that were interpreted as originally clastic sediments, they contain units which we interpret as felsic members of, which we interpret as metamorphosed bimodal volcanics. They look like you can see them on this figure. So we have the felsic layers shown in here, just alternating with amphibolites. They are all partly migmatitic. So what we did is that we have collected samples from several of these units, as you can see here on the map, in different parts of the coastal terrain. We separated the zircons and we dated them by the secondary ion mass spectrometry. And here are the results of the dating of these bimodal volcanics. You can see that the age of this volcanism spans between approximately 818 million years up to something like 785 million years. So this is the age of the bimodal volcanism, which is associated with the clastic sedimentation. If we look at the same type of rocks that appear today in the Foreland, in the Congo craton cover, you can see that there are also several places where we can collect the felsic members or intermediate members of the volcanic rocks that are sitting within the clastic sedimentary rocks that are now metamorphosed. And if we date these volcanic rocks, we can see a different time span, now more like 740 up to approximately 410 million years. So the volcanic activity that we see within the metasediments on top of the Congo craton shows this time span in here. If we go back to the coastal terrain, we were also interested into the detrital zircon data from there because we wanted to see where the sediments came from. So we collected several samples of quartzites or biotite gneisses, which we believe that they represent the clastic part of the volcanosedimentary sequence. And we looked at the ages of the detrital zircons that we have separated from them. The same we did in the cover of the Congo craton for metasedimentary samples that somehow go together with those volcanics that I was just talking about. We separated zircons from them, and we also dated them to see the age spectra in these samples. And here are the results of the detrital zircon dating. In the upper part of the slide, you can see the results from the coastal terrain. In the lower part, you can see the results from the Foreland, from the central Kaoko zone and the orogen core. And what we see is that we see two contrasting types of samples. These are pooled data for several samples. Always, here is the number of the zircons dated. And we see that always in the lower or tectonically lower part of these metasedimentary units, we see age spectra that look like this. We see basically a bimodal distribution where we have strong peaks that are Paleoproterozoic in age, somewhere between 1.7 and 2 billions, and then a very wide spectrum of ages that gives Mesoproterozoic ages, usually between something like 1 billion and 1.5 billion. And this is the same for the coastal terrain and for the central Kaoko zone and orogenic core, so for the foreland. The second group of the samples, which represents the upper part of the metasedimentary sequence, we see that the situation is very different. The Paleoproterozoic and Mesoproterozoic signals, they are very small, and the entire population is dominated by Neoproterozoic clastic zircons with two peaks, one that is close to 1 billion and the other one which is somewhere around or between something like 800 and 750 million years, which, if you remember, is the age of the volcanic rocks that are accompanying the lower part of the metasedimentary sequence. In case of the Congo Craton cover, we even start to see a very prominent peak that gives us the ages of approximately 650 million years. And again, if you remember, I told you that these ages represent the timing of the coastal terrain early intrusive magmatism and also the timing of the migmatitization in this unit. If we move still farther to the east, we come into this so-called Eastern Kaoko zone, which is represented by the lowermost great metasedimentary rocks. And also in this part of the belt, we did some detrital zircon study. The problem here is that we do not have any volcanic rocks that could be dated and that could tell us something about the timing of the sedimentation in here. However, we have clastic metasediments that represent complete stratigraphic profile, and luckily we have present two glaciogenic units which were correlated with the well-dated global glaciation intervals. So the lower one represents the Sturtian glaciation, which took place between 660 and 716 million years, whereas the upper diamictite represents the Marinoan glaciation, which took place approximately between 635 and 645 million years. So what we did is that we collected several samples along this entire succession, and we looked again at the detrital zircon age record in these sedimentary rocks. And I will present 4 samples here, one from below the Sturtian diamictites, one from within the Sturtian diamictite, another one from the unit that is sitting directly between the Sturtian and Marinoan diamictides in this profile. And finally, one sample that we dated, or where we looked at the detrital zircons, that is situated directly above the Marinoan interval. So here are the data, and you can see how the detrital zircon changes as we go from the bottom to the top of the entire sedimentary sequence. So here in the lower part, which is represented by these two samples, one from below the Sturtian diamictide and within the Sturtian diamictide, you can first see that the situation is very similar to the data that we have from more westerly units. We have this like a bimodal distribution. We see strong Paleoproterozoic signal between something like 1.8 and 2 billions. And then we have another very rich population of Mesoproterozoic zircons spanning the interval somewhere a little bit below 1 billion up to something like 1.4 billions of years. As we go higher up in the sequence, you can see that the Mesoproterozoic signal disappears, and we have basically only the Paleoproterozoic signal. And this we interpret as a gradual disappearance of the Mesoproterozoic units that are sitting on top of the Congo craton, which we know has the magmatic rocks in the age interval between 1.8, 1.75 and something like 2 billions. And this signal is dominating in this part. If we come above the Sturtian diamictide and below the Marinoan diamictide, you can see again that the situation changes dramatically. We see almost no signal from the basement, and what we see again is this strong Mesoproterozoic peak around 1 billion, and then signals coming from the volcanic rocks that we saw being associated with the metasediments of the coastal terrain at about 800 million years. If we come directly above the Marinoan diamictide, we can see again the peak at 1 billion. We see a peak of approximately 800 million years, which is the signal most likely coming from the metavolcanics in the coastal terrain. And we even see the peak of zircons with ages around 650 million years, which for us represents the signal coming from the magmatic or migmatitic rocks of the coastal terrain again. So, what do all these data tell us about the timing of the crustal stretching, and finally about the termination of the rifting? And another question, what do we know from the sediments themselves about the way in which they were deposited? I just want to repeat here that these authors consider the timing of the continental breakup, meaning the end of rifting and the beginning of the opening of the Adamastor Ocean at approximately 780 million years. However, our data show that we see episodic synsedimentary igneous activity, which is still compatible with active crustal stretching at 840 up to 770 million years in the coastal terrain, and between 740 and 710 million years on top of the Congo crater. There is another very important information which comes from the Otavi platform that sits directly on top of the Congo crater. And this unit or this region shows that the sediments show change in subsidence rate compatible with the rift-drift transition between approximately 660 and 645 million years, somewhere here in the stratigraphic column. And what is important, that this is the time interval between the Sturtian and Marinoan glaciation. So what the sedimentologists see as the end of active stretching of the continental crust, at the same time, we see a major change in the provenance of the clastic metasedimentary rocks. And we see that whereas below this transition from the Sturtian into the Marinoan glaciation, we see signals that are compatible with the erosion of the Congo craton basement, whereas above this and before the Marinoan glaciation comes, we see that we have the sediments sourced from completely different units, and the data suggests that the source actually comes from the exhuming coastal terrain. So what is the conclusion for this? The onset of collision in the Dom Feliciano, Kaoko, Gariep orogenic system was estimated at approximately 600 million years ago by Frimmel et al. And Bassey et al. But our data show that we see the deposition of an orogenic flysch shortly before approximately 645 million years. By other words, shortly before the onset of the Marinoan global glaciogenic interval. So it means that the collision in this orogenic system, as we discuss it here, started not at 600 million years, but something like at least 45 million years earlier. So, what would be the conclusion for this part of the talk? We see that in the Kaoko, Dom Feliciano, and Gariep orogen, the end of rifting in the Kaoko belt took place somewhere between the end of the Sturtian and the beginning of the Marinoan glaciation, so sometime between 660 and 645 million years ago. We see that already before the onset of the Marinoan glaciation, we see the deposition of early flysch, early orogenic, synorogenic sediments on the African side of the continent. So these data suggest the maximum lifetime for the Adamastor Ocean in the south to be something like 15 million years, which gives us 7.5 million years of opening and 7.5 million years of the closure again, when we can start to see the orogenic sediments on the African side. So with the half spreading rate of 2 centimeters per year, as we discussed this before, this gives us oceanic crust, which would be at maximum 300 kilometers wide, and not those 2,000 or even up to 5,000 to 6,000 kilometers, as it was estimated before. The question is whether the oceanic crust has really developed. I don't actually believe it for the northern part of the Kaoko Don Feliciano Gariep orogen, but we believe that remnants of this incipient oceanic crust appear abducted on top of the rift-related sedimentary rocks in the southern part, where we today see the Gariep Belt in the southernmost Namibia. Okay, these conclusions bring me to the second part of my talk, which I would like to devote to the orogenic evolution of the Kaoko Don Feliciano Gariep orogen. And at the beginning of the second part, I would like to ask 2 questions again. The first question will be, when actually started the orogenic evolution of the Kaoko Don Feliciano Gariep orogen? Here I'm bringing back these reconstructions of the pre-orogenic setting of the system. And if you look at them, most of them, if not all, they suggest that the end of subduction took place at approximately 600 million years. Another thing that is important is that each of these reconstructions contains this unit here, which most of you most likely know as the so-called Granite Belt of the Don Feliciano Belt. And it is a vast unit of huge amounts of granitic rocks that some of the authors interpret as roots of magmatic arc that has developed above the subducting Adamastor Ocean. And I would like to ask this second question, whether the Granite Belt really represents a magmatic arc or not. So this is the setup for the second part of the talk, and let's have a look which data we can present to answer these questions. So first of all, a little bit about the structure of the northernmost Don Feliciano Belt. Just like in the case of the Kaoko Belt, here we can also talk about the orogenic hinterland and the orogenic foreland. The orogenic hinterland is here represented by the so-called Portobello complex, which is this small unit in here, represented by approximately 800 million years old migmatitic basement to the granite belt. These rocks were described by Giuseppe De Toni in his paper from last year. And we also know that this unit contains some intrusions of the age of 650 million years, and the migmatization of this unit is most likely of the same age. I just want to emphasize that these ages, the age of the basement and the age of the migmatization and the early magmatic activity, is exactly the same as what we have seen in the coastal terrain of the Kaoko Belt. So these two units are obviously related, and that's why we both put them as the orogenic hinterland. Then we have the granite belt itself. And what is important to say here is that it shows the igneous activity in the time interval between 630 and 580 million years, and especially this age of 630 of the earliest magmatism belonging to the granite belt will be very important for us, but I will emphasize this later. This unit, the granite belt, is interpreted either as a late Neoproterozoic arc above the subducting Adamastor Ocean, as I said. This is the interpretation of Miguel Basset. But, for example, Fatima Bittencourt and her group, they interpret this magmatism as a result of sin to post-collisional magmatism. So again, let's see which arguments we can add to this dichotomy. The orogenic foreland is represented by several tectonic units that are exposed to the northwest from the granite belt. The tectonically lowermost unit is represented by the Camboriú complex and also by the São Miguel complex, which both are Paleoproterozoic basement, which has an affinity to the Luis Alves block or Luis Alves craton, exposed still farther to the northwest. The Camboriú complex is covered by metamorphic rocks of the Brusky complex. These are approximately 800 up to less than 650 million years old, rifting-related volcanosedimentary rocks. And currently, the age of metamorphism is not known very well. We only know that it must be younger than something like 650 million years, which is the age of the oldest so-called late orogenic granitoids that include the Brusky complex. This is what is sometimes called the Valsungana granitic suite. If we want to look at the early tectonometamorphic evolution of the Brusky complex, we have to look at metamorphic rocks that show the oldest structures. And these are within the Brusky complex, exposed in its southwestern part, where we see the oldest flat-lying metamorphic fabric, which we call S1 in this case. And this metamorphic fabric, in some places, not very often, contains stretching lineation that is oriented northwest-southeast. And this lineation and this metamorphic foliation, sometimes shows kinematic indicators that are compatible with top to the northwest oriented thrusting. In this part of the Brusky complex, we see the metamorphic rocks with the highest metamorphic grade when it comes to this metasedimentary unit. These are the garnet-bearing mica schists, and when Jack Percival studied its metamorphic conditions, he was able to model the stability field of the metamorphic assemblages in the samples that he collected, and the modeling gave him metamorphic conditions between 5.5 and 6.5 kilobars and metamorphic temperatures of something like 540 up to 570 degrees of Celsius. The presence of garnet in these samples is very important for us, because what we did was, or what Jack did again, was that he separated garnets from some of these samples, and he dated them by the lutetium-hafnium method. For those of you who are not familiar with this method, it is the isochron method that provides the timing of the early growth of the garnet, because garnet is the phase that strongly fractionates lutetium during its early growth. So we believe that with this method, we are dating the early growth of the garnets in our sample. And Jack studied 2 of them from the southwestern Brusky complex, and the dating gave him 2 ages. For one sample, he got the age of 653 million years plus minus 4. For the other one, he got a slightly higher age of 660 million years plus minus 2. On top of that, Jack also looked at some other chronometers. One of the mica schists contained monazite, which we dated, and we obtained 2 age groups for 2 different groups of grains. The grains, the geochemistry of which was compatible with the garnet stable in the rock, we obtained the age of formation of the monazite 641 million years. For the other group of grains, the geochemistry of which is more compatible with the garnet dissolution, we got an age of 584 million years. So the older age we interpret as the age of the peak metamorphism of the Brusky mica schists, whereas the younger age is somehow related to some post-peak metamorphic processes connected with the dissolution of the garnet. Finally, from one sample, we were able to date also biotite by the argon-argon method, and by this chronometer, we obtained a cooling age of 635 million years, which we interpret as the time of the final exhumation of the mica schists, and they're cooling below the temperature of approximately 300 degrees of Celsius, which is the closure temperature for biotite. So, to sum up these data that I had just presented, we see that the metamorphic conditions of the Brusky complex mica schists with garnet show a typical orogenic apparent thermal gradient of approximately 25 degrees per kilometer. And these values are typical for the process of crustal thickening. So we haven't seen any high pressure metamorphism in this part that would be somehow compatible with subduction related processes. The lutetium hafnium dating of the garnet gave us 660 to 650 million years. And as I said before, this approximates the timing of the onset of crustal thickening in the foreland of the Northern Dome Feliciano belt. Finally, the uranium-lead monazite age of 640 million years dates the metamorphic peak, which is for us the moment when the Brusky mica schists have reached the greatest depth. At the very end, we also were somehow able to constrain the cooling of this part of the Brusky complex, which we dated at approximately 635 million years. And for us, this age says that the Brusky complex is exhumed and cooled down below the temperature of 635 degrees. So the important conclusion from these data is that the orogenic crustal thickening lasted from approximately 660 up to 635 million years. So which conclusions can we draw for the northern part of the Don Feliciano belt and its orogenic evolution? So, by other words, what are the answers to those two questions that I have posted at the beginning? When started the orogenic evolution there? The orogenic evolution is dated, or the onset of the orogenic evolution is dated by the early garnet growth at approximately 660 and 650 million years. The second question was whether the granite belt can represent magmatic arc or not. Again, our dating shows that the emplacement of granitoids of the granite belt started approximately 20 to 30 million years after the crustal thickening and the development of the metamorphic foreland in the northern Don Feliciano belt was already taking place. So it means that the intrusion of the granites of the granite belt can by no means be related to the subduction, because it, or the granites, they originate well within the orogenic period already. So the crustal thickening in the lower plate in the foreland was caused by overtrusting of the orogenic hinterland, and such evolution rules out the possibility for the granite belt being a magmatic arc. So which conclusions I can draw for my entire talk? What did I say, or which arguments have I presented for largely intracontinental character of the Kaoko, Don Feliciano, and Gariep orogen? First of all, you have seen the data from the Kaoko belt, which show that the end of active crustal stretching or rifting took place between 660 and 640 MA. We have also seen that the synorogenic flysch sedimentation in the Kaoko belt started after the end of the Sturtian and right before the onset of the Marinoan global glaciation, which means also between 660 and 640 million years. So you can see that the end of the crustal stretching, which should be followed by breakup and development of the Adamastor Ocean, is immediately replaced by orogenic activity, orogenic evolution, which allows the sedimentation of the synorogenic sediments. This is confirmed by the data from the Don Feliciano belt, where we have shown that the crustal thickening started at approximately 660 to 650 million years again, and all these age estimates for these various processes suggest that there is simply no time for development of a large oceanic domain between the African and South American forelands as we know them today. So, rather than subduction-related evolution of the southern part of the South Atlantic orogenic system, we believe that what we are looking at is actually an inverted rift system, inverted Neoproterozoic rift system, which closed due to the closure of some oceanic domain, which was, however, exposed farther to the west of the present-day South American foreland, represented by the various units that are a part of the larger Rio de la Plata craton or of the Luis Alves craton in the north. And I believe that this is all that I wanted to show you today. Thank you very much for your attention and your interest into my presentation. And I believe that we still have some time for questions, which I am ready to take and which I am ready to answer. Thank you very much.
Então, essa foi a apresentação do Giri. E vamos... Já chegou a Luana aqui também. Olá, Luana, tudo bem?
Oi, tudo certinho, Augusto?
Tudo certo?
Tudo certo.
Vou adicionar também o Giri agora.
Ok.
Hello.
Hello, everyone.
Hello, Giri. How are you doing?
Fine.
Great talk. We all like it very much. So, Augusto, do we have some questions for Giri in the presentation?
Still, we haven't got any here. No, I think people, pessoal, se quiser comentar em português ou em inglês, a gente vai traduzir.
The guys are shy, and also today is holiday here in Brazil.
Yes.
I see. Okay.
But while nobody's asking something, so I want to ask you something, Giri, because I don't know if I got it properly from your talk, but
Yes.
You said that you consider that some of the ophiolites that you have in the African side can be considered the register of oceanic crust or something like that. So I have one question for you. What do you think about the ophiolites that the guys as Lau Hartmann and Ednei Quester and their students also are always documenting over Rio Grande do Sul, for example, and that they are oceanic crust remnants, or what means ophiolites?
Yeah. The situation is as follows. You know, the pieces of ultramafic rocks and associated mafic rocks in various positions within the Don Feliciano belt, as far as I know, they always occur within units that contain metasediments. And in several places, these metasediments were shown as being related to this rifting period that we know that it took place between something like, let's say around 800 million years and up to the something like 650, maybe a little less, say 660 or something like that. And my opinion is that small remnants of the mantle and associated mafic rocks are very often known also from either hyperextended continental margins or some deep simply rifting related basins that were inverted afterwards, so that they of course come from the mantle, but they say nothing about their association with a true oceanic crust that has developed. So they are, of course, as I have also learned, you know, these rocks are nowadays also classified as ophiolites, but they are not ophiolites in terms of what we probably learned when, or at least I learned when I was a student, with this like complete stratification of the oceanic crust. So, and it happens all around the world. I know several examples from from where I come from the Bohemian Massif, for example, where we clearly see that such units are not related actually to the fully developed oceanic crust, but just to the partial exhumation of the mantle during rifting, but not necessarily during opening and growth of an ocean.
Okay, and I don't know that much about the isophyolites from the African side. So in the African side, you have this sequence more complete and more signatures and the other features that we need?
Not really. Even I do not know like very well that area in the southern Namibia, though I started to work there 3 years ago. But the area is very difficult to access, actually not in terms of really going there, but because it's on a land that is owned by the diamond miners. And, to get all the permits and stuff like that, it is a bit complicated. However, I know the works of colleagues who originally defined these units as remnants of oceanic crust. So it is likely that they are correct. On the other hand, if I look at the area in detail, I still cannot be 100% sure that we are indeed looking at oceanic crust. The situation that I am talking about is that there is like an allochthonous unit that is dominated by metabasalts. And in some places, there are also like mafic plutonic rocks, of course, partly deformed, not very much, but somehow deformed, associated with this. But honestly, I can also imagine that they actually represent let's say basalt flows or original basalt flows and associated mafic intrusions within an extending continental crust. It is very hard, very difficult to say to which stage of the evolution of the passive continental African continental margin it really belongs. So, but I have no clear arguments to disprove the interpretation of these colleagues. So I don't want to say at all that they are wrong. I would be absolutely happy with their interpretation. I have no problem with it. In the southern part of the entire system, I can easily see that a small ocean has developed, has opened, but still I do not believe that it was an extensive oceanic domain, even down there in the south.
Not a kind of Atlantic Ocean or something like that.
No, definitely not. Yeah.
Okay. Ophiolites are polemic. Precambrian ophiolites are more polemic than everything.
Yeah, probably. The thing is that, if I would see because this is already interpreted as oceanic crust, the allochthonous unit in the Gariep Belt in the south. So if I would see, really pieces of mantle, then the gabbros, then the relics of sheeted dikes and stuff like that, and then the metabasalts on top, then there would be absolutely no doubt. But from what I have seen, but I admit I haven't seen much, it doesn't really look like this typical profile through evolving oceanic crust.
Yeah, the whole section and everything is so well preserved in such scenario of deformation, and then everything is pretty hard to find.
Yeah,
but it's good to know.
Yep.
We have another question here from Giuseppe, and I'll show.
Hello, Giuseppe.
Yeah.
It's kind of a
Well,
complicated
yes,
question.
yeah. I'm just trying to summarize what Giuseppe means by this question. Hello, Giuseppe. Nice to hear from you. Of course, I do believe. My understanding, my current understanding is that the subduction that is responsible for the development of the São Gabriel arc in whatever time period. I know that you have a very long history recorded by the geochronology in the São Gabriel arc. However, I believe that this subduction process is the one that basically governs the entire history of the Dom Feliciano belt. So it is from the rifting period, and then finally into the convergent history and into the actual orogenesis, which, as you have seen from my presentation, and also from your or now new Matthäus's data, which started at around 660 million years or something like that. What is the, of course, we can discuss what is the exact contribution to it. That, or we both know that you have a different view a little bit than I have, but I think that we both agree that the subduction that most likely happens to the west of the Brazilian foreland of the Dom Feliciano belt is the critical feature in the development of the southwestern margin of Gondwana, in fact. First, rifting of the Rodinia, and then the convergent evolution that leads to the formation of Gondwana.
Augusto?
Yeah. Yes. Another question here from Matheus Battisti. Do you know if the geochemical signature of the 740 million years volcanic rocks of Congo cover are similar to the 790 million years CA, or are they maybe juvenile arc rocks as those in São Gabriel arc?
Yeah. Hello, Matheus. Thanks for this. This is something I luckily know something about, and the answer is no. They are different. So we know that for the roughly 790 up to 800 million years, the geochemistry is different. It has geochemical signatures. As far as I know, you have to be aware that you're not talking to a geochemist. But as far as I know from my work together with Vojta Janošek, they have mild geochemical signatures similar to what is seen in the magmatic arcs. They have also very different neodymium model ages and things like this. I just want to say that when I say that they have mild signatures similar to magmatic arc, we still interpret it in a different way than being in any arc or back arc position or something like that. If you look at the volcanics on top of the Congo craton itself, then they have clear affinities to the extension of the continental crust and melting of the subcrustal mantle. So there is no signature related to subduction that could be interpreted as related to subduction. There are different epsilon neodymium signatures and stuff like that. As I said, first, I'm not geochemist, and I tend to forget things. So I just want to encourage you to look at our 2018 paper about the is it this one? Yeah, it must be this one. And also another paper about the rifting-related sediments in the Kaoko belt, where we looked at both of these types of meta-igneous rocks, and where Vojta did very thorough geochemistry. So you can compare the geochemical signatures of these two age groups that we see in the Kaoko belt.
This is 2018 paper, I guess, where you talk about the bimodal volcanic rocks, and then you add that although they can be close to magmatic arc sources, they should be more related to lithospheric mantle melting by extension, relating to drifting or something like this.
Because, the main thing that we still didn't discuss in any of our papers really closely, and it's mainly because nobody works in it, and it is that I have a suspicion that the early Neoproterozoic, the Tonian rifting, actually starts in the remnants of the Mesoproterozoic crust that was somehow present between the Congo Craton, which is Paleoproterozoic, and the old units that you have in the Dom Feliciano, like is the Luis Alves, like is the Nico Perez, and all these small occurrences of the basement that you have along the foreland. And we, of course, know very well that there is a substantial portion of Mesoproterozoic crust in the south along the western edge of the Kalahari Craton. And I am now almost sure that it extends to the north, or it extended to the north. We have some relics of it in the Kaoko belt, but most likely the possibly largest occurrences of these rocks are now thrust under the coastal terrain. So basically underneath the hinterland of the Orogen in the north. So it's not accessible for us anymore.
And then sometimes you just find the inheritances or xenocrasts or something like this that are indicating that you have some relation of melting of these units to generate the igneous rocks, the Tonian ones, and then
exactly. And on top of that, if you look at the detrital zircon signals in any rocks that we now interpret as rifting related, doesn't matter whether it is on the Kaoko side or whether it is in Santa Catarina, that's work of Jack Percival, the recent one, or in Rio Grande do Sul, you see everywhere a very strong Mesoproterozoic signals. It's like a half of the population is always like this, and we simply almost do not have corresponding rocks exposed nowadays.
The ones that were upper became sand, and then the others that go down became granite, so we don't have them anymore.
Yeah, exactly.
Nice. And Giuseppe asked, where is the suture?
Well, how do you define a suture in this case, or which suture you want to see? I believe that if we want to talk about suture, then the suture is west of the São Gabriel block, and it's hidden under the Paraná sediments. But as we go farther to the north, the situation becomes much more complicated, because there, I believe that we have another extensive rift system which is inverted, and that's the southernmost Ribeira belt. If you go there, because then behind it you have the south of the how it's called, that craton, you know, São Francisco, exactly, thank you. And then only behind the São Francisco craton you have the rocks that are equivalent to the São Gabriel, and only then there I would look for a suture, and then next to it is the Amazonian craton, which is today, basically, as far as I know, the only exposed continental mass that, in my opinion, is responsible for the final closure of this entire rift system that we look at along the coasts of the Atlantic. Also, if you look at, sorry.
Yeah, just while you were talking, Giuseppe said the suture he was referring to, that is the real one.
Yeah, yes. Thank you. So this is what I just said, you know, that's what I mean. If you look at our Adamastor paper, then, you know, there is this like a subduction system west of the São Gabriel and west of that similar arc unit in the Brazilian belt, in the Brasilia belt. It is shown there, you know. So the suture for me is the Trans-Brasiliano lineament. But we are far away, of course, you know. But I mean that this is the mega structure that is responsible or that somehow traces or might trace the closure of what you call the Charrua Ocean, or what other people call, you know, the Circumrodinia subduction, or Russian colleagues, they call it the Mirovoy Ocean, and so on. There's many names, you know, hanging in the literature. But the main problem is, or what has to be emphasized, I guess, is that the presence of the future of the suture, or the position of the suture with respect to the position of the Dom Feliciano belt, the distance between the belt itself and the suture is much, much smaller in the Rio Grande do Sul than it is in the north, you know, in the Santa Catarina, where the Dom Feliciano belt actually somehow obliquely ends towards the Congo craton, and then, you know, the Ribeira belt takes over. But of course, it's all hidden in the under the Atlantic Ocean in the shelves. So hard to say.
Do we have more questions, Augusto?
No. I think these were the questions.
Okay. Okay, guys, then thank you very much for inviting me again. I really apologize that I was late, but I obviously miscalculated the hours, you know, so that's the problem, and I apologize for it, you know, so that if you were waiting for long for me, then it's obviously my fault and my mistake.
No, it was exactly.
It was perfect.
Yeah. Okay.
Yeah. Good timing. Yeah. And Giuseppe wants to have a beer with you, just to say here.
Thank you, Giuseppe. Of course, I miss you all very, very much. You know, I miss my trips to Brazil very, very much, and I hope that the situation will improve soon.
Yeah, I will let the discussion about the granites and the extension and the transpressive structures that we have for a beer in another time. it's enough for today. It was a very, very good talk. Thank you so much.
Okay, thank you guys.
Thank you.
You guys, and have a nice rest of the meeting, and see you at some stage.
Thank you so
everyone.
much, Giri.
Okay, bye-bye.
Bye.